Ladies and gentlemen, good afternoon. It's truly a delight to be back here at the Future Congress in Santiago. I have spoken here several years running, and as you heard in the introduction, very kind, thank you, that I have normally addressed topics of life, the universe, and left out the everything. This time you're going to hear about the everything. I should just say that I very much wish I was in charge of the $100 million that Yuri Milner a few months ago devoted to the subject of SETI, the search for extraterrestrial intelligence. Alas, I am only on the advisory committee, but nevertheless, it is wonderful to be associated with a subject that for many years has had very little money to spend and suddenly has been transformed by this magnificent gift. But my job here today is not to talk about searching for intelligent life in the universe, but of opening up a completely new window on the universe by a new physical principle. And the subject I'm going to be discussing is gravitational waves. Why did I choose this Congress to address the subject of gravitational waves? The answer is that it is almost the exact centenary, because 100 years ago, last month, Albert Einstein gave a lecture at the Prussian Academy of Sciences in Berlin. And remember, this was in the middle of the First World War. So most of Europe was engulfed in killing. But for Einstein, who at that time was a Swiss citizen, he wasn't involved in the war. And he continued doing his work into the theory of relativity and the theory of gravitation. And it was in December 1915 that he presented the equations that describe his general theory of relativity. And the equations are there at the bottom of the screen. And even if you don't know any mathematics, you can tell that these are very simple equations. Yet right from the start, it was clear that Einstein's general theory of relativity, which we just call general relativity, that Einstein's theory was actually very, very hard to understand and very hard to work with. And the reason for that is because Einstein's description of gravitation differs completely from Newton's theory of gravity. In Newton's theory, one object, like a planet, acts on another object, like another planet, with a force across space. In Einstein's theory, it's not like that at all. Gravity isn't a force. It is a warping or a distortion of the geometry of space-time. Just think space. Warped space. And you know about that because you've all seen Star Trek and the warp drives. Well, that's where it comes from. It comes from Einstein 100 years ago, warped space. Here's a picture, an attempt to describe warped space. Now, at that time, there weren't very many observational facts that Einstein could point to in support of his theory. A lot of people were skeptical about this strange theory of gravitation. How could it be tested? Well, Einstein gave details of one particular test that could be done. If gravity warps space, then the sun's gravity should create a space warp around it, and a star beam passing close to the sun would be bent, and perhaps it would be possible to detect that. Here is a picture explaining how it works. Imagine that you're an observer on the Earth, and you're looking at a star which is labeled A, and the sun is very close to that star in your line of sight. Then if Einstein is correct, the light will be bent as it passes close to the sun, bent by the warped space. And the position of the star in the sky will slightly change. It's like putting a lens up to the sky, or think of looking at the sky through the bottom of a milk bottle or a jam jar. All the positions of the stars change. It's a very, very tiny effect. But in 1919, Sir Arthur Eddington, who was Britain's leading astronomer, decided that he would go on an expedition to Brazil to observe the bending of starlight during a total eclipse of the sun. The problem about seeing the bending of a starbeam is that the sun is so bright you can't see the stars close to it, except when there is a total eclipse. Then the sun's glare is shut out and you can see the stars in the daytime. And so he was able to do that measurement, and it was that, more than anything else, that made Einstein an international celebrity. And this is how the New York Times chose to present the evidence. See how it explains. Lights all askew in the heavens, all this strange language. Men of science, more or less agog over results of eclipse observations. Einstein's theory triumphs. After that, I think a lot of people became convinced that Einstein's theory was correct. Now, it's interesting to note that in the year 2019, almost to the month, the exact centenary of this famous observation, there will be another eclipse of the sun, and this map here shows the path of totality in blue, and you see that the only substantial landmass that it intersects is here in Chile. So I think it will be a wonderful celebration of 100 years since Einstein's prediction was tested to have an event here in Chile to celebrate that subject 100 years later. Now, although in 1919 this was very new, today astronomers are very familiar with the warping of space. Look at this picture. This is sometimes called an Einstein ring. And it comes about because light is bent around the bright object you see in the foreground by the space warp that surrounds that object. But it's bent in every direction. So imagine that there's a galaxy directly behind the one we're looking at. Then the light from that galaxy is bent all around, it's called gravitational lensing, all around to create that ring-shaped effect. So that's an example. You can see with your very eyes space being warped. You get that type of image. Now, I mentioned that Einstein's gravitational field equations, the equations of general relativity, are very hard, not just because they described a curved space-time, but because they are difficult mathematically to solve. They're easy to write down, very simple to write down, very hard to solve. But Einstein was one of the first to realize that you had to use approximation. And I like to think this very week, 100 years ago, but I can't be sure, it might have been last week or next week, he was working on an approximation to his field equations. And in May of 1916, so nearly 100 years ago this year, he presented a new idea in another lecture. And this idea was the possibility of gravitational waves. It's the first time anybody had used that term. This is an English translation of the paper he gave on June the 22nd, 1916. The possibility of gravitational waves. Now, I've said to you that gravity, for Einstein, is a distortion in the geometry of space. So gravitational waves are ripples in space itself. Imagine that the very geometry of space, even if there's nothing there, just empty space, a gravitational wave passes through, it's ripples in the geometry of space. What an incredible idea. Einstein knew that these waves would travel at the speed of light. And the question is, could we detect them? Now, it's interesting that in that same paper that Einstein first predicted gravitational waves, he got, as we say in English, cold feet. That is, he was not sure that this was real. These waves seem like ghost waves. Could they really be there? As a note at the end of his lecture, it says, the reason that they are not real waves, but rather apparent waves, is because of some complicated mathematical thing. He predicted them, but then he said maybe they don't exist. Well, he was wrong. They do exist. And I'm going to tell you how they can be detected. Now, you're all familiar with electromagnetic waves, like light and radio waves. And this is how you make light or radio waves. You'll be familiar with radio antennae of the type there you see on hillsides. And to make radio waves, all you have to do is make an electric current go up and down in the antenna, just like that, and the radio waves spread out. I think everybody knows that basic idea. You generate radio waves by disturbing electricity. Gravitational waves are very similar. You make gravitational waves not by disturbing electricity, but by disturbing gravity. All mass is a source of gravity, so any disturbance to mass will generate gravitational waves. I'll give you an example. That makes gravitational waves. As the weight swings around and around, gravitational waves come off. Should be easy. Why can't we just do that in somebody's laboratory and detect the effects of gravitational waves? Well, there's a fundamental reason why it's much harder, and that is because gravity is so weak. I've actually taken the trouble to write down for you how weak. And the answer is that gravity is 10,000 trillion times weaker than electricity. We know electricity is very powerful. It can exert very strong forces. We run trams, we run trains on the force of electricity. Electromagnetic forces are very strong and very noticeable. We don't run anything using gravity, not gravitational waves anyway. But gravity does exert a force, and this force was measured a long time ago by a physicist called Henry Cavendish at Cambridge University in 1797. What I'm showing here is a simplified version of the essential idea. If you suspend two 1 kilogram masses 1 meter apart, you can measure a tiny force of attraction between them. How tiny? Well, it's equivalent to the weight of a grain of pollen held in your hand. That's pretty small. But nevertheless, it can be measured. So objects, even in the lab, exert a gravitational pull on each other. But to create noticeable gravitational waves, you need a much stronger gravitational field. Where do you go for that? What about the Earth? Well, that's stronger. The Sun, stronger still. But the good thing about gravity is it gets stronger as the distances get shorter. So if you had a star with all its mass and shrunk it down to a very small size, the gravity near the surface would be very, very strong indeed. And we know stars like that. They're called neutron stars. They occur when the core of a large star runs out of fuel and the star explodes. It's called a supernova. And the core of the star collapses to form a ball of neutrons. Even the atoms are crushed into neutrons. So they're called neutron stars. And imagine something that's got the mass of the sun, maybe 1.5 suns, but squashed into something the size of Santiago. This would be a bad day for Santiago. So we're talking about a star the size of a city. The gravitational forces at the surface of such a star are so big that a teaspoonful of matter weighed on that star would weigh more than the Earth's continents weigh here on Earth. Very intense gravity, very large space warp, very good potential for gravitational waves. Now, one neutron star on its own can emit gravitational waves, but a better system is when you have two neutron stars, like this, orbiting around each other. This is often called a binary neutron star system. And as the stars orbit around, so they emit gravitational waves, and the energy transported away in these gravitational waves causes the orbits of the stars to decay. So they spiral into each other, a death spiral. Here we see it again. The binary object creating gravitational waves and spiraling together. Now, I've called this one binary pulsar because sometimes neutron stars are detected by radio pulses that they emit as they spin. And there's one such system that's been studied for many years. Because the pulsar pings are so accurate, it's possible for astronomers to follow exactly the decay in the orbit of this binary system, the binary pulsar. Now, physicists can calculate the rate which energy is being lost according to Einstein's predictions. They can use Einstein's theory, 100 years old, to work out how much energy should come off and how fast the orbits of the stars should decay. And they can compare the observations with the theory. And here's the comparison. You see, it's perfect comparison. So we have every reason to believe the binary pulsar is emitting gravitational waves exactly in accordance with Einstein's theory, 100 years old exactly. That gives great confidence that gravitational waves really exist. But what we'd like is to detect not just their effect on the transmitter, but detect them here on Earth. Imagine that it was the 1860s, 1870s, that Maxwell had predicted the existence of electromagnetic waves, of radio waves. Nobody had detected them. But supposing somebody built an antenna, a transmitter, but nobody had built a receiver. And they said, look, when I plug in the transmitter, my electricity bills go up. So some energy is being given off. And we can work out that the energy that's emitted is exactly what my electricity company says I should pay. Then you think, well, yes, it's probably something's coming out of that transmitter. But nobody had detected radio waves with a receiver yet. Well, we're in that situation. We've seen the emission of the waves, we haven't detected them. Now, what else might produce gravitational waves? Well, here's one thing. This is a supernova explosion. So I explained to you that heavy stars will burn out and their cores will collapse. And this is one source of gravitational waves. There you get a great burst of waves. And this is a picture of a supernova in a distant galaxy. For a while, it outshines the galaxy. Here's another picture, and this is a supernova that was seen to explode in the year 1054, and it's called the Crab Nebula. And when you look at that today, there's a neutron star, indeed a pulsar, in the center of that cloud of gas. And incidentally, in a story that the next lecture is going to pick up, you will hear about the importance of this process for life in the universe by disseminating the element carbon around the interstellar spaces. So these are the sources of gravitational waves we know about. How do you go about detecting them? Well, gravitational waves are passing right through us as we sit here. It's a very creepy thought. They're going right through you and right through the Earth. But their effect is so weak, we don't notice it. But if you could have an enormous gravitational wave, this is what it would do to you. One moment it would make you shrink that way and expand this way, and then in the next part of the cycle you'd shrink that way and expand that way. So it's a very simple idea. It means that the gravitational wave, simply by changing the geometry of space in a periodic way, would show up as a vibration in any object you can think of. That's actually not the way scientists are trying to detect gravitational waves. They're using a fancy laser system. And so what they like to do is to send a laser beam down a tube for many kilometers. It reflects back again, and they do the same down another tube at right angles. And if a gravitational wave comes along, it will stretch one tube, shrink the other tube, and you can tell by comparing the light that this has happened. And this is called a gravitational wave observatory. This particular one is a photograph of LIGO in the United States. There are two of these. Laser Interferometer Gravitational Observatory. Europe has one called Virgo. And the big news about LIGO and Virgo is they've recently been upgraded. Just very recently, in fact. This is from September last year. Hunt for gravitational waves to resume after massive upgrade. Let me tell you an almost unbelievable statistic. To detect gravitational waves from objects like the binary pulsar on a once-a-month basis, roughly, you have to search a big volume of space. To detect those, it's necessary to measure a change in the distance of the arms of the interferometer, which are several kilometers long, less than the size of one atomic nucleus. Imagine that. Or another comparison is the relative change in the distance is equivalent to a human hair in the distance to the nearest star, 4 1/3 light years away. They have to detect such tiny, tiny changes, and they can do it. They now have that capability. A few weeks ago, there were rumors circulating that advanced LIGO had indeed seen gravitational waves. What can I tell you about that? I'm a theoretical physicist, but I have friends who work on this. I can't tell you their names. And when I ask them, are these rumors true? What I'm told is, not only will I not reply, I won't even let you mention my name to say that I've been asked. So it's that sensitive. But any day now, there could be an announcement from Advanced LIGO that yes, finally, after several decades of searching, we've seen the first gravitational waves. Now, before I finish, I should mention one other thing that you may have picked up from the news media 1 year ago. I've mentioned that supernova explosions and binary pulsars are a prolific source of gravitational waves, but the biggest source of all is the Big Bang itself. That created enormous amounts of gravitational waves. But they're very hard to see because those gravitational waves are now millions of light years in size. So how do you detect gravitational waves from the Big Bang? Well, you use the universe itself as a detector. And this is a detector at the South Pole that has been involved in that. One way you can do it is to use the heat radiation coming from the Big Bang. This is the fading afterglow of the origin of the universe 13.8 billion years ago. And this radiation, as you see, has a lot of structure. And if gravitational waves were made during the Big Bang, they would leave an imprint in this structure. But that imprint is very hard to see. It shows up not in variations in the heat, but variations in or patterns in the polarization of the radiation, the heat radiation from the Big Bang. Here is a distinctive such pattern. The problem is that dust, humble dust, in the foreground, that is in our region of the Milky Way, makes patterns like that too. So to see gravitational waves from the Big Bang, you first have to subtract the effect of dust in our neighborhood. And so far, it's not been possible to disentangle the two and say that we have detected gravitational waves from the Big Bang. So here, I'm leaving you with a story that is beginning. It's not ending. This is the beginning. The detection of gravitational waves will be the end of the story, the 100-year wait since Einstein predicted it, but it will be the beginning of a new era in astronomy, will be the beginning of gravitational wave astronomy. You see, we have two windows on the universe for ground-based astronomy. We actually have one or two others, like neutrino astronomy, but traditional astronomy, we have two windows. And Chile is preeminent in both of those. We have optical astronomy and we have radio astronomy. Two windows or two eyes on the universe. The development of gravitational wave interferometers would open up a third window on the universe, a third eye. We could then see the universe with three eyes rather than two. And so my take-home message, which is more political than scientific, is that every new window on the universe leads to a surprise and to new discoveries. Will Chile be part of the coming era of gravitational astronomy, just like it is a major player in optical and radio astronomy? That is up to you people here in Santiago to decide. Are you going to buy into this exciting new branch of astronomy? Ladies and gentlemen, thank you very much.